Hi all. In this video, we are going to learn about this very interesting concept called deep learning, and we will see how this is different from usual classical machine learning. So in usual classical machine learning, be it using logistic regression or support vector machines or artificial neural networks, essentially what you have is a set of inputs which maps into a set of outputs, and your objective is to learn this hypothesis function which can help you in mapping a new input to its suitable output. So here these input values are basically called the features of your problem. So these are the features and these are the outputs. So for example, if you want to predict whether a person is going to have heart disease or not, your features could be the cholesterol value, sugar value, the body mass index, and other such parameters of the person's physical structure. Similarly, if you want to, let's say, predict whether a particular person is going to buy your new car or not, you can use that person's annual income, the previous cars he or she holds, the amount of money he or she spends on holidays, and stuff like that. So these could be some kinds of features which can be eventually mapped to the desired output. Now here the issue is that for many problems that come under this domain of machine learning, these feature values are not clearly available. So for example, if you want to do face recognition and you want to identify if a given face belongs to your friend or not, then what kind of features do you use? Do you use the color of the 20th pixel? Do you use the number of edges? Do you use the contrast in the picture? What do you use? It is not very clear. Or for example, if you want to do text classification, so let's say you have some piece of text in English or Hindi or Bengali or any other language, and now if you want to do some kind of a sentiment analysis on that piece of text, it is again not very obvious that what kind of features would you use. So in classical computational linguistics domain, there are some features which are known to work for a wide variety of problems, like n-grams and stuff like that. But that doesn't work always, and especially as your problem becomes more complicated. For example, when you want to do language translation, for these problems, it is not obvious what kind of features one may use for learning this mapping between the input to the output. And this is where deep learning really comes in. So if you clearly know what features you are going to use to get your desired outputs, then that constitutes what is called classical machine learning. But if you do not know the features, then you are in the domain of deep learning. So essentially, what deep learning is all about is your artificial neural networks plus representation learning. So what do we mean by representation? So conventionally, as I just mentioned, in classical machine learning, you extract various kinds of features from your given data and then use that to find a mapping between the input and the output. But in representation learning, instead of identifying such clearly defined features, you try to represent your image or your text in a certain format that makes it more accessible for machine learning to work. And here there is a serious problem and a serious limitation of deep learning, which we are going to discuss in somewhat more detail later on, is that these representations do not correspond to specific features. So if you have learned a way to represent your given image or text in a certain format, which is usually called embedding, that doesn't necessarily correspond to a particular feature that may make sense to you in an intuitive real world sense. And because of that, deep learning algorithms are often called black box algorithm because they work very well, they give you very good accuracies, but you do not exactly know what is it that the algorithm is learning, or on what basis is the algorithm doing the classification that it is doing. Now, one more important point to note is that deep learning is not applicable to all problems. So broadly speaking, deep learning was inspired by computer vision, natural language processing, and speech processing. There are, of course, other problems where deep learning is applicable, but not everywhere, because there are many, many problems in real life where you exactly know the features that you want to use, and you just want to use machine learning to figure out the functional relationship between the set of features and the set of outputs. But in particular, in this domain of computer vision, which largely represents image and video processing, and natural language processing and speech processing, is where you do not a priori know what features you want to use, and so you want to learn some kind of representations for doing your given classification. So deep learning algorithms have been available since a long time. Actually, even in the 80s and the 90s, people did propose deep learning algorithms, but they were kind of not very useful for almost 20 to 25 years. And suddenly, over the last decade or so, deep learning has become very, very powerful. And that is primarily because of the availability of GPUs, which are graphical processing units. Now, deep learning algorithms are very, very computationally expensive. And so running them on conventional CPUs is not at all effective. It takes days and days and days to run. But GPUs make it extremely parallelized, which make it easy to run a deep learning algorithm over reasonable time frames, or maybe hours, or sometimes even minutes. And that is why deep learning algorithms have become very, very popular nowadays. But it is very, very important to understand that just because deep learning is very popular and it is talked about a lot, it doesn't mean that all machine learning has become deep learning. No. And just because your machine learning algorithm is complicated, and just because your artificial neural networks has 20 layers, it does not become a deep learning algorithm. Because if you precisely know the features that you are going to use, then you are still doing classical machine learning. It's only when you do not know the features and when you are learning certain representations of your given input for doing the classification that you are in the domain of deep learning. So as I said, deep learning was primarily inspired by computer vision, NLP, and speech processing. So let me just give you a very brief overview of what are some of these popular algorithms. Now there are, of course, a lot of variations which have happened over these algorithms, and so almost every month you have some new advance which is happening. So without getting into all those changes, let me just give you a very brief idea about the overall picture of what these algorithms try to do. So essentially, when we talk of computer vision, we are talking of spatial data. When you take an image, that is a spatial data, whereas NLP or speech processing is temporal data. So here, let me classify data into two kinds. So data for deep learning. So one is your spatial data and one is your temporal data. So here one could say that your temporal data is just one-dimensional spatial data, and that is true in a sense. But still, when you have temporal data, which comes, for example, for NLP and speech, there you have kind of long-term relationships between the various points in your data. Whereas spatial data, which is largely for images and videos, there the long-term relationship is not present, because if you have a face, it is there in some region of your image, and if you have a, let's say, a dog in another part of the image, that is not necessarily connected to your face. That's a different object which is there in your image. But when it comes to temporal data, then if you, let's say, have a sentence or a paragraph, there could be more intricate relationships between these different words which are present at long distances. So because of that, there are two different sets of algorithms which have developed in the deep learning community. So for spatial data, generally, the algorithm used is CNN, or what is called convolution neural networks. So this C stands for convolutional and NN is your neural networks. So of course there are many variations which have happened over CNN, but largely CNNs are the default choice for analyzing spatial data using deep learning. When it comes to temporal data, as I said, you can think of temporal data in the form of a one-dimensional spatial data, in which case your one-dimensional CNNs are also applicable. But generally, there are other methods which are specially designed for handling temporal data. And the first one in this category is what is called RNN, where the R stands for recurrent neural network. So there is also something called a recursive neural network. So that is not this RNN. So here we are referring to recurrent neural networks. Then there is a variation over RNN which is called LSTM, and then there are also these things called GRUs. So LSTM stands for long short-term memory, and GRU stands for gated recurrent unit. So again, we are not going to get into too many details about these algorithms, but I'll just give you a brief overview of what these algorithms do. So in the case of CNN, convolutional neural networks, essentially what you do is that you take an image, for example. So here let's take a 2D image, which basically means a collection of pixels. So let's say you have these different pixels over here, and each pixel has some value. If it's a black and white image, it will have only one channel, but if it's a colored image, it will have a red, blue, green channel. So irrespective of that, it is basically a collection of pixels which have a spatial distribution. So what you do in convolution neural networks is that instead of analyzing the entire image at one go, you take different chunks of your image. So it can be a 2x2 piece or a 3x3 piece or a 4x4 piece, but you take these different chunks and then you compute a convolution of this chunk with a certain weight matrix. Okay, so you perform convolution of this portion with your weight matrix of same size. These weight matrices are also sometimes called filters in the convolution neural network. So this is a different way of processing your input data till you reach your output data. So in a regular ANN, you took these different input values and then you passed on to the hidden layer, to the second hidden layer, to the third hidden layer, and so on till you reach the final output value. So here these weight matrices correspond to your hidden layers, but instead of doing a computation which is a linear computation passed through an activation function in regular ANNs, here you compute a convolution function which has been found to give you more accurate results. And here to emphasize on the most important point, so when you are feeding an image to a CNN algorithm, you are not specifying which features to use in your image. So these weight matrices or these filters automatically figure out which features to use. But again, the important difference is that these weight matrices or these filters do not correspond to obvious features of the image. So if you analyze these weight matrices or filters after your learning algorithm is done, you cannot precisely say that what aspect of the image was used for your classification. And that is what makes these CNNs kind of a black box. So although a lot of research is going on to understand how to decipher or how to extract this feature information from the CNN layers of the filters, but so far not much progress has been made. RNNs or recurrent neural networks work in a very different manner. So when it comes to recurrent neural networks, we are basically talking about temporal data. So let's say if I write, I am a human being. So here, this is a sentence of 5 words, and even the first word is connected to the last word. So in the case of an image, we could take these small chunks and analyze them separately. But in the case of this temporal data, you cannot do that because there can be long range dependencies. And this is what separates your temporal data from your spatial data, and that is why you need different methods to analyze this. So now if you, let's say, wanted to analyze this using a regular artificial neural network, what you would do is that you will feed this information into some kind of an ANN, and from there you will get some kind of an output depending on what particular kind of classification you want to do for a given feature. Now the important thing about these regular ANNs is that in ANNs the information flows only in one direction. So you start from the input, you go to the hidden layer, you go to the next hidden layer, and so on, and finally you go to the output. So here the artificial neural networks is not explicitly trying to understand the relationships between different parts of the sentence. So here what we need to do is that we need to take these nodes of the hidden layers which are being computed using the given input values, and we need to find a way to pass on this information across the various nodes of the hidden layer. So instead of the information just flowing from the input to the output through the hidden layer in unidirection, we also do passing of information along this direction, so that the temporal information from the first word can actually pass on when the last word is also being processed, so that the relationships between different parts of the sentence can be understood in a better manner. So I'm not getting into the details of RNNs and what it actually does and how it actually processes these things, but this is the fundamental principle of RNN, that instead of the information just flowing in one direction from the input to the output, you also have a cross flow of information which is in the order of the temporal data, which helps you in understanding the relationships between different parts of your sentences. Now this relationship can also be bidirectional, so you could have, for example, another layer of hidden layer nodes in which your information is passing in the opposite direction. Now these are called bidirectional RNNs and have also been found to be very useful for solving a wide variety of problems. But one limitation of these RNNs is that if you, let's say, have a very long sentence, then by the time this information reaches the last node, it can either vanish to zero or it can explode to a very high number. And that is because essentially all these passing of information is multiplication of matrices. So if the entries of those matrices are less than 1, then as you keep multiplying them, the values tend to get smaller and smaller. But if the values of those matrices are larger than 1, and if you multiply lots of them, then the value will tend to become very large. So that is the problem of vanishing and exploding gradients in your RNNs. So in order to solve that, there was a variation of RNNs which was proposed, which is called LSTM, and a similar method which is called GRU. So LSTM stands for long short term memory and GRU stands for gated recurrent units. So again, without getting into a lot of details, essentially the concept of LSTM and GRU and the variation is that instead of just mindlessly passing this information across all the nodes of your hidden layer, what LSTMs and GRUs do is that they intelligently figure out that which information needs to be passed along till the end and which information needs to be forgotten. So it is this ability to differentiate between the information that is relevant and needs to be remembered and the information which is not relevant and can be forgotten is what gives LSTMs and GRUs their real power and applicability over the conventional RNNs. However, one problem with LSTMs and GRUs is that they are still sequential. So if you have, let's say, a temporal data, then you still need to analyze them in a given sequence, which prevents their parallelizability, which makes it difficult or rather almost impossible to write these LSTM algorithms using parallel programming. And if you cannot do parallel programming, your algorithm is going to become very, very slow. So although LSTMs and GRUs are very useful, they are a very intelligent method of analyzing temporal data, but they are very, very slow to run because they cannot be implemented in a parallel fashion. In order to take care of this limitation, there is a new method which has been developed over the last few years and which is now taking the internet by storm, and that is called transformers. So again, without getting into details of the transformers algorithm, what a transformer does is that it extracts the relevant information about these dependencies between different words of a sentence without needing to do a serial computation. So it allows for massive parallelization of your algorithm, and because of which your power of LSTMs and GRUs still remains intact, but it does the processing in a very different manner so that the relevant information can be extracted in a parallel manner. So now these deep learning algorithms are of course very, very useful, very, very powerful, but they have some important limitations, and because of which deep learning algorithms have also come under criticism. Now, whether that criticism is severe or not depends on which side of the river you are on, but still those criticisms are valid enough to be taken into account. So let's look at some of these important limitations or criticisms of deep learning. So the first and important limitation, which I have also mentioned, is that they are very resource intensive. So there was a study that was done recently which found that these deep learning algorithms can sometimes be more polluting than the vehicles on the road. And that is a serious cause of concern because, okay, you can develop lots of computational resources and you can allocate money for that, but the side effects in terms of pollution can be far reaching and cause long-term damage to the environment. So, deep learning is important for human progress, but one has to be careful about when to use deep learning and to what extent should we use it. The second very important limitation or criticism of deep learning is the lack of explainability. So what happens is that, in the case of classical machine learning, although it is difficult to figure out exact function which the machine learning algorithm is using, but at least you know what features it is using. And you can figure out which of those features are playing a more important role in the final classification. However, in the case of deep learning, even that information about the features is gone because you are feeding raw data to your deep learning algorithm and it is figuring out those features on its own, and the features that it figures out are usually very, very abstract and they do not make any intuitive sense to humans. And this is a serious problem. For example, when you come to medical diagnosis, you can use deep learning algorithms to figure out whether a person has a certain disease or not from the images of various organs and muscles of the body. But if you do not know which features that algorithm is using, it becomes very unethical to actually deploy it for doing medical diagnosis because a patient will finally ask the doctor that, on what basis are you saying that I have a disease? And if the doctor cannot give a good answer, it's very likely that the patient is not going to take that doctor seriously. And so, this lack of explainability may not be a serious problem in all areas of deep learning, but at least in the medical diagnosis area and some other areas, it is very, very important. For example, if you have a driverless car, which is, running on the roads without any human driver, and there is an accident, then who is going to take responsibility for it? If you cannot explain why the car made that mistake and ran into an accident, it is very difficult to pin down the responsibility on a particular person, and that leads to various kinds of legal and judicial issues. The third important problem is the inherent biases in prediction. Now, it so happens that, because you do not know what features your deep learning algorithm is using for doing the classification, sometimes it can learn features which are absolutely ridiculous. For example, if you use a deep learning algorithm for analyzing the CVs of applicants for a job that you have advertised for, it may be learning features that have no relevance to the job itself. For example, if you are in a company which makes, let's say, mechanical engineering parts, so in the past, if you look at the history of your company, it is likely that there were more men who worked in your company than women. But with changing times, women are getting better educated, so they are also, now equally good at doing all these tasks. And now let's say, if a lot of women start applying to your company, but because your algorithm is based on the past history of your company, and which shows that mostly you are a male dominated company, it may just start rejecting females because, it has learned to be biased towards men. And that is a serious problem. Even in the case of admissions, there are some universities who have tried using deep learning algorithms for sorting out the CVs of various students who apply to the university, and it was found later on that, some of these features that the deep learning algorithm is using could be very, very biased and does not actually reflect what the university is really looking for. And these, biases can be very, very problematic and lead to various kinds of ethical issues which must be avoided. The fourth problem is of cyber threat. Now, as these deep learning algorithms start getting deployed more and more for various tasks, and because we do not really understand what features they are using, they can be fooled very easily by your adversaries, and you won't even know why exactly that happened. And the fourth limitation, which is not really a limitation, but still, let me state it for the sake of completion, is that deep learning still relies on human micro work, which means labeling of data at least. So when you want to learn a particular function between the input and the output, and let's say for the sake of images, you have a set of images and you want to classify them into, let's say, a human face or a monkey face, there of course you need humans to be able to label those images to begin with, because if you don't even have label data, then how do you use machine learning to learn which is a human and which is a monkey? And this is kind of a limitation because deep learning algorithms are huge algorithms and they require huge amounts of data to work, and because huge amounts of label data is not available, it becomes difficult to train these machine learning algorithms reliably. So it would be nice if you could, let's say, come up with a deep learning algorithm that can work with small amounts of data. So that brings us to the domain of one shot learning or few shot learning, so that you do not have this over dependence on human micro work to generate large amount of label data. So I hope this brief introduction to deep learning gave you a sense of what deep learning is all about. Finally, before I end, let me make just one important remark that although deep learning algorithms have become very, very smart and they can do some things that are absolutely incredible, but still, despite all these advances, DL is still weak AI. In an earlier video, we had spoken about strong AI and weak AI, where the strong AI is, human-like intelligence with self-awareness and deep learning, no matter how advanced it gets, but it will still remain in the domain of weak AI. Strong AI is a completely different thing, and no matter how advanced these algorithms become, they are not really going to get into the domain of strong AI. Strong AI requires a completely different perspective which currently we are not aware of. But this important distinction is important to remember that deep learning algorithm, no matter how advanced, either now or in the future, is still in the domain of weak AI. So with this, let me end this video, and I hope this will motivate you to learn these various algorithms of deep learning in more details, and you will have more fun with machine learning.